Hello everyone. Welcome to my YouTube channel VLSI Learn with Fun. Here I will teach you every VLSI topic in a funny manner so that you will remember it forever. So let's get started with today's topic.
Hello everyone. Welcome to my channel VLSI Learn with Fun. Hemanth here, and in today's session, we will discuss something that every beginner asks. Bro, I wrote my RTL code. It's simulated perfectly. Now what? If you've ever stared at your Verilog code and wondered, how does this become an actual chip, you're in the right place. Today, I will take you all through a journey from RTL to silicon. And trust me, it's more dramatic than a Tollywood movie. So grab your chai, settle in, and let's dive into the world of physical design. Before we start, let me tell you what you'll walk away with me today. By the end of this session, you'll understand the complete flow from RTL to tape-out, all 7 critical stages of physical design, and why engineers keep saying, bro, it's iterative. If you know RTL, Verilog basics, and digital logic, you're ready. It's just 15 minutes, short, sweet, and packed with learning. Also, one thing, this is a beginner-friendly session. No boring textbook language here. I will keeping it real and relatable. What will you gain from this session? The ability to finally answer that interview question, explain the physical design flow. Let's go. Okay, imagine this. You've written your RTL code, beautiful, clean, simulated perfectly, and expecting a chip from fabrication team. But here's the truth, is RTL is just the blueprint. Think about building a house. Someone given you the contract to build. You designed a blueprint. You can't hand a blueprint and say, here's your house, right? Need to construct. Same way, you can't give RTL to a fabrication team and expect a chip. Blueprint is your RTL code, the idea, and construction is like physical design, making it real. There are 7 stages between RTL and a working chip. Skip even one stage, your design fails. Think of it like making Hyderabadi chicken biryani. You have the recipe, RTL, but you need to prepare ingredients, layer rice, cook in dum style, add raita, skipped adding chicken. It's a disaster. That's exactly what physical design is, the step-by-step cooking process that transforms your recipe into actual biryani. I mean, silicon. Let's break down these 7 stages using the 5 W's framework. Before we dive into the steps, let's answer the fundamental questions. What is physical design? The answer is transforming RTL gate-level netlist into a physical chip layout that a fabrication team can manufacture. Where? It happens from synthesis output to the final GDSII file. That's the file the fabrication team needs. When? After RTL synthesis, before tape-out to fabrication. Why? We need it because a fabrication team needs physical coordinates, metal layers, power grids, not just logic. They're building nanometer-scale structures. In which way we can implement physical design? It happens through 7 critical stages. Let's explore each one. Here's your roadmap how to implement physically designed from RTL. 1. Synthesis, the translator. 2. Floor planning, the skeleton. 3. Placement and routing, the construction. 4. Clock tree synthesis, the nervous system. 5. Static timing analysis, the judge. 6. Verification and sign-off, the final approval. 7. Tape-out, the handoff. Each stage has a purpose. Each stage can make or break your chip. Let's go through them one by one. Step 1. Synthesis. This is where your RTL code gets translated into gates. Think of it like Google Translate. You give input, RTL, Verilog, or VHDL, which is human-readable, and get output, gate-level netlist, which is machine-readable. But it's not just translation. It also optimizes for 3 things. Timing, can it run at your target frequency? Area, how much silicon space? Power, will it turn into an oven? The goal of synthesis? Create an optimized gate-level netlist that meets all your design constraints. This netlist now goes to the next stage, floor planning. Step 2, floor planning. This is the most critical step. Have a question? Why? Because floor plan is like your chip's skeleton. Get it wrong here, everything else suffers later. But what happens in floor planning? Here, engineers decide chip dimensions, shape, size, create the power grid like electricity lines in a city, and then define regions for different blocks, RAM here, CPU there. Let's understand how with an example. You are organizing an expo event. Analogy: you wouldn't buy land and start building without a proper plan, right? First, you decide the plot size, then where to place the rooms, the entrance, the kitchen, and the parking area. Because if the floor plan is bad, you'll end up with narrow walkways, poor ventilation, and endless rework. It's the same with chip design. Before you build, you must plan the chip layout carefully. Just like placing the kitchen near the dining area, you don't want to place high-speed memory far from the CPU. Floor planning decides chip size, block locations, and structure. Goal is to minimize wire length between communicating blocks. Because longer wires equals more delay, equals timing violations, equals pain. Step 3. Placement and routing. Okay, now the real construction begins. There are two parts here. Placement. You take all those gates files from synthesis and place them physically on the chip, and also optimize positions to minimize wire length. Think of it like arranging furniture inside your house. The rooms are already built, now it's time to place the bed, table, and sofa. If related items are too far apart, movement becomes slow and daily life feels inefficient. Similarly, in physical design, placement ensures that standard cells are positioned close to the ones they communicate with most, optimizing speed and efficiency inside the chip. Routing. Now connect all the gates with wires, metal layers. Follow the netlist connections. Avoid congestion, too many wires in one area, traffic jam. Real analogy like Hyderabadi metro construction. Placement is deciding where each station goes. Routing is laying the actual tracks between stations. You optimize for shortest paths, avoid crossings, and manage traffic. The three enemies are congestion, timing, and DRC violations. Goal is every cell placed optimally, every connection routed cleanly. This stage takes the longest time, especially for complex designs. Step 4. Clock tree synthesis. This is the nervous system of your chip. The problem? Your chip has millions of flip-flops. All of them need the clock signal. But if some get it late, disaster. Clock skew is when different parts of the chip get clock at different times. Think of a water supply system in an apartment building. Water from the main tank must reach every flat on every floor at the same pressure and at the same time. If the 10th floor gets water late or with low pressure, while the first floor gets it instantly, residents face chaos and complaints. To fix this, engineers add booster pumps and branch pipelines at key levels to balance the flow. Similarly, CTS adds buffers and balances the clock network so that the clock signal reaches all flip-flops simultaneously with minimum skew, keeping the chip perfectly synchronized. If all flip-flops don't get clocked together, your chip doesn't work. CTS solution: build a clock tree like branches, balance all paths, ensure zero skew or minimal. Goal is every flip-flop gets the clock at nearly the same time. Get this wrong? Your chip might work in simulation but fail in silicon. Step 5. Static timing analysis. This is where the judge enters. After placement, routing, CTS, you think you're done? Not so fast, bye. Static timing analysis checks, will this chip actually run at the target frequency? What does static timing analysis do? Analyzes every signal path in the design, checks setup time, hold time violations, gives you a pass or fail. Ever wondered why trains have schedules? Train data must arrive before departure time, clock edge, setup. Train must not leave early, data must be stable, hold. If timing fails, you go back to optimization. Resize cells, bigger drivers, faster gates. Adjust placement, add buffers. The truth is timing closure is iterative. You rarely get it right the first time. If timing has ever ruined your day, welcome to the club. Goal is to verify all paths meet timing, chip operates at target frequency. Step 6. Verification and sign-off. This is the final checklist. Before you send your design to fabrication, 3 judges review it. DRC, Design Rule Check. Does your layout follow fab rules? Minimum spacing between wires? Minimum width of metal layers? All physical constraints met? LVS, Layout versus Schematic. Does your physical layout match the netlist? Every connection present? No shorts, no open circuits? STA, Static Timing Analysis, again, final timing check after all changes. Indian analogy like engineering college exam results. All 3 exams, DRC, LVS, STA, must all pass. Even if one fails, back to the drawing board. No backlogs allowed before graduation, tape out. If any check fails, go back to the problematic stage, fix the issue, re-verify, iterate. This is why physical design is called iterative. Multiple iterations are normal. Don't panic if you don't get it right the first time. Goal is to ensure design
is manufacturable, error-free, ready for fab. Step 7 is manufacturable, error-free, ready for fab. Step 7, tape out. This is it, the finish line. Your design is verified, signed off, ready. Tape out means generating the final GDSII file and sending it to the fabrication unit. GDSII is the blueprint for the fab. It contains all geometric information, layer-by-layer details, every coordinate, every polygon. It's like submitting your final year project. You've worked for months, tested everything. Now you hand it to the examiner, the fab. No going back. Once you tape out, the design is frozen. The fab takes over, and after weeks or months, your code becomes silicon. This is where the magic happens. Now, let me tell you the painful truth about physical design. There are 3 enemies that are always fighting. 1, area, smaller chip equals lower cost. 2, power, less heat, longer battery. 3, timing, faster clock, better performance. The problem, you can't optimize all 3. It's like the famous engineering joke. Pick any 2. Want fast and low power? You need big area, expensive. Want small and fast? High power, overheats problem. Want small and low power? Slow, poor performance. Every VLSI engineer has to make trade-offs. It's like choosing toppings on your pizza. Want everything? It'll be expensive and heavy. Want light and cheap? Fewer toppings, less taste. This is why experienced engineers are so valuable. They know which trade-offs to make for each design. Mobile chip, prioritize power and area. Battery life matters. Server chip, prioritize timing and power. Performance and cooling. IoT device, prioritize power and area. Tiny, long battery. Understanding this triangle will make you a better designer. Okay, time for some real talk. When I started learning physical design, I thought, I'll do synthesis, then floor plan, then placement. Boom, done. Wrong. Here's the reality. You rarely get it right the first time. Common scenarios, timing violations, go back, resize cells, adjust placement. Routing congestion, go back, adjust floor plan, rethink block placement. DRC violations, go back, fix routing, adjust spacing. Power issues, go back, add power gating, optimize logic. Multiple iterations are normal. Think of it like cooking biryani. First attempt, rice overcooked. Second attempt, spices too much. Third attempt, perfect. Experience helps you converge faster. Senior engineers might need 2 or 3 iterations. Beginners might need 10 to 15. Don't get discouraged. Every iteration teaches you something. As they say in cricket,
Practice makes perfect. And one suggestion for all who want to take a career in VLSI is to take a long-term training so that you will understand everything in detail. Now the question everyone asks, bro, how long will this take? It depends on design complexity. Small design, 10,000 gates, like a simple calculator, 2 to 4 weeks. Medium design, 1 million gates, like a microcontroller, 2 to 3 months. Large SoC, 100 million gates, like a smartphone processor, 6 to 12 months. Plus, multiple respins if issues are found. Real example, Apple's A-series chips, years of development. Your college project, few weeks. Key lesson, patience and persistence are required. Don't rush. Always choose quality over speed. A working chip after 6 months is better than a broken chip after 2 months. Let's talk about tools. You need industry-standard EDA tools for this. Commercial tools are expensive but powerful. Number 1, Cadence Innovus for place and route optimization. Number 2, Synopsys ICC2 for advanced PR, physical synthesis. Number 3, Mentor/Siemens Calibre for DRC LVS verification. Number 4, Synopsys PrimeTime for STA, static timing analysis. And the cost? Crores of rupees per year. So for learners, open source alternatives. OpenRoad for complete flow, Magic for layout editor, Yosis for synthesis. Pro tip, learn on open source tools first, then transition to commercial tools in industry. Most companies use Cadence or Synopsys. These are industry gold standards. All right, let's wrap this up with the key takeaways. Number 1, RTL is just the beginning. Physical design is where your code becomes silicon. Number 2, there are 7 critical steps: synthesis, translator, floor planning, skeleton, placement and routing, construction, clock tree synthesis, nervous system, static timing analysis, judge, verification and sign-off, final verdict, tape-out. Number 3, iteration is normal and expected. Don't panic if you don't get it right the first time. Number 4, 3 enemies: area, power, and timing. You can't optimize all 3. Learn to make trade-offs. Number 5, sign-off is the judge's verdict. DRC, LVS, and STA must all pass before tape-out. And number 6, timeline varies from weeks to months. Most important, this is where real VLSI learning starts. If you've made it through a complete physical design flow once, you're no longer a beginner. And that's a wrap. Thank you so much for joining me today. I hope this session cleared up the mystery of what happens after RTL. Remember, physical design is a journey, not a destination. Every chip you've ever used went through these exact steps, and the engineers who do this, they're the unsung heroes of technology. Keep learning, keep designing, and remember, your code will become silicon someday. If you think the video is informative, give it a like and share with your fellow members. Subscribe the channel for more such topics. Thank you.